Welcome friends, welcome to the next lecture on cache memory. So, the reference for today's discussion will also be the same, the William Stallings book, and a few things from the Hennessy and Peterson. Right? Okay. So, before we start today's session, I hope that you have already seen the last lecture, and I would love to hear some feedback regarding the lecture, because I'm also new to this particular platform. I have never done my recording before, and whether it was too slow or like it was fast or it was like boring. So I would love to hear that so that I can incorporate in my next video. And of course, in today's class, you will able to see the the title of the slide. So anyway, let us start. So as we often do, that before starting the lecture, we revise the last lecture. So what we have seen in the last class is essentially the introduction regarding the cache memory. So you can see there are two terms here. One is cache, another one is memory. So memory is a storage device, you know that, it is storage, right? Now if you talk about cache, you have already seen cache in many places. For example, your browser, right? Well-known place where it caches the recently accessed web pages, it caches the DNS, domain name server mapping, which maps from the name to the IP address. So if you write google.com, so the name Google will be associated with an IP. So that mapping is called a DNS mapping. So it stores that so as to get the things faster. So why do you use cache in case of browser, let's say, to make the things faster, and we bring things closer to our place of uses, right? So that's what the basic essence of caching something, to bring something closer of their use. And when it's about memory, so it is between the processor and the main memory. All right, then we have seen the motivation behind using cache memory, right? And then we have seen the overall functioning of cache memory, what happens if a request comes from CPU, what will you do? And then we have also seen a few terms related to cache memory, right? Like hit, miss, hit rate, miss rate, hit time, and miss penalty, right? Okay, now today's discussion will be basically on cache mapping, right? Okay, now let's say before let's start with that. So we already know where does cache sit, right? So where does cache sit? Cache sits in between processor and your memory. Now if you look at the book, you'll get this kind of picture where this is your processor, this is the main memory, right? And the cache is supposed to be placed in between this. Now there is another block which is called MMU, right? So the full form is Memory Management Unit, right? So just to give you some idea regarding that, see, you can see processor is using something called logical address, right? But the main memory is using physical address. So these two addresses are not same, right? So there comes something in between. You need to convert this logical address to the physical address, and that is essentially done by this MMU, to be very short. Now, why is it so? Just to give some, throw some light on that. Though this comes, you will be getting these things in your operating system course to a great detail, right, under the heading called virtual memory, right? So, as far as this course is concerned, so let me throw some light on that. So what happens, if you recall the previous classes, we know that processor executes multiple programs, multiple applications. Now each application will have its individual address space or process address space. If you remember, there's a question on mid-sem also, I guess, or in one of the quiz regarding the virtual address space. So to make things simple, let's say we are using 1, 2, 3 applications, so 3 processes. So each one will have its individual address space. Let's say someone says 100. So this 100 address will belong to process 1. The 100 will also be applicable for process 2, and process 3 can also say 100 address. But actually the 100 will be only one place in main memory, right? But process 1 is saying 100. This 100 is very different from the 100 of process 2, right? So then how do you do that? So that means there must be some way, if process 1 says 100, it must be some location, maybe some X. When process 2 says 100, it can be some other location, right? Let's say Y, right? So this is essentially is being done by this particular unit called MMU. Now, as far as cache memory is concerned, if we place cache before MMU, so that means this is working on logical address. So this cache is also called virtual cache, right? Essentially, it's not virtual, the cache exists, but the cache working or the address of the cache, deals with logical address. Now, if the cache, come to the second part of the diagram, or other B, if the cache is placed after MMU, then it works on physical address. So that means this organization of cache is called physical cache or physical address cache, right? So this is just to give you an essence, but for our discussion we won't be considering MMU in between, and we'll be thinking that CPU generates only one address and that address is being seen by main memory, right? It's a straight line, same address, right? Okay, moving ahead. So we have seen this diagram in the last lecture also, right? So this says that this is a logical view of main memory. It is being organized as blocks, block after block, and each block will have individual words. Now, one block will be mapped to one particular block or line in cache. Another question is, see, the size of the cache is smaller, it's quite obvious. Now the size of main memory is larger. Another question is, which block from main memory will come to which cache line, right? Or which cache block, because it can contain only, let's say if it can contain only C number of lines, right? But it has 2 to the power n minus 1, which happens to be a larger one. Now what will you do? How will you do that, right? So this is essentially handled by something called mapping, right? So the mapping, cache memory mapping, deals with this particular problem, right? So it says mapping decides how a block in cache is associated with a block in main memory, right? Now from your intuition, you can think that there cannot be only one way. There can be various ways, right? So typically there are three types of mapping in this case. One is direct. So direct says, well, though we'll discuss, let's say, so there are three types of mappings: direct, associative, and set associative, right? And each one will have its some pros and cons associated with that, right? And we'll see in the subsequent slides, we'll see these mappings in detail. So let's come to direct mapping. So direct mapping means very simple. Each block of main memory maps to only one line in cache, right? So how do you say that? Say you have the main memory, right? Main memory, right? Now main memory will have, let's say, let us take one particular block. Now this particular block can go to only one particular block in cache, right? So this mapping is fixed. There is a dedicated there will be a dedicated block in cache for every block in main memory, right? Now the question comes, as you know, that the size of main memory will be huge, right? So if we talk about only one block in cache, so this block may be associated with, let's say, this particular block. That's fine. So there has to be other blocks in main memory also which will be associated with this cache block, because its size is fixed. Let's say if you have 16 number of blocks, right? So this might have let's say 160 number of block, right? So after every 16, this will be quite natural to repeat that. But the main point is that this is fixed. So you will see that this block over here in the cache can be associated with only this block, maybe some other block, right? No other block can come to this particular cache. That's what is direct mapping, right? If we consider this simple mechanism where the cache line number, that will be found out by a mod of with total number of cache lines. So if you have 5, in the last example, you have 16 number of cache lines. So you divide by which one, you divide, or rather you take a mod with 16, right? Suppose you are given in main memory, you are given, let's say, 150. So then what we'll do? We'll take 150 mod 16, right? So whatever is the number, so that will be, the cache line for this particular 150, right? Okay. Now if that is the case, you'll see that one cache line 0 will be associated with main memory 0. Cache line 1 will be associated with main memory 1, and so on and so forth. This will go. Once you reach to the last line in the cache, then the next, the next one will be associated with again the cache line 0. So what is the next line or next block in memory? Is the M, right? So then essentially the 0 will be associated with block number 0, M, twice M, thrice M, so that way, right? Similarly, block number 1 will be associated with 1, block number 1 in main memory, M plus 1, twice M plus 1, right? So on and so forth. Now, suppose a request comes, right? Request comes for, let's say, block number some 2M, right? Or 2M plus 1. So when it comes when the block number is 2m plus 1, so you'll be very sure that it can be at this position, right? Or other way, if some let's say 3, if you know that the cache line is 3, so then that means the 3 can be, or other, let's say to make it simple, let's say cache line is 1. So that means if the cache line is 1, so you know that this cache line may come from the 1 memory, block number 1 of the main memory, or it can come from m plus 1, or it can come from twice m plus 1. So we need to see for these addresses or these locations, right? The things will be more clear in the next slide. Okay, here we come. Now, what happens in case of direct mapping? How the, whatever we have said just now, it's a diagrammatic representation of that. So CPU request, as it does, CPU will request for a memory address, right? It requests something from this memory address. That something can be an instruction, the something can be a data, right? So now this this memory address, looking at this memory address, we have to decide where in the cache this particular thing can belong, right? So how will you do that? This is to be done by you have a the whole memory address. The tag will come little later. Its whole memory address will be divided into 3 parts. One is the word, one is a line, and is a tag. Now this line bit will tell from where in the cache you might get this particular item, right? Now, as you know, the word, every line or every block contains multiple words. We have already seen. So this is also present from this diagram. So this is one line 0. This contains multiple words. So this word will be given by the bits in this particular word, right? Then the line, so to the next few bits will tell where in the cache you will get the particular, you might get this particular item. Now this line bit, as you can see, this line bit will depend on the size of the cache, right? If you need to search, let's say 16 location, if you have 16 blocks, right? Because you know the size of the cache, so from there we'll know the size of the number of blocks in the cache or number of lines in the cache. If you have 16 lines, then will be only 4 bits will be required to go for the particular line in the cache. Now if you recall from the last slide, that one particular line 1 might contain these several things, right? And the several things will have different addresses, right? Now how to get that? This is done with the help of something called tag, right? So essentially it says when you get the line number, you will get that, okay, if this is to be there in the cache, this has to be there in this particular block or particular line. Now the only thing is to check whether the bits stored in this particular tag matches with my requested tag or not, right? So to make these things more clear, let us go to some explanation. Let's say the CPU generates 6 bits of let's say I'll come to that in the next mapping. That will be more that will be more clear to you, right? So just going with the discussion once more, if the requested item is to be there in the cache, so it will be there only in the line identified by the line address of this particular, the requested address. Now the question is, this line might contain might be from some other places also, some other locations in the main memory also, right? So to get that confusion clear, we'll be doing a tag comparison. The tag which is associated in this particular line along with the tag that is being requested by my CPU. So that's a comparison logic. If this matches, so that means whatever item is there is essentially the requested one. So that is the hit. Otherwise, that will be a miss, right? If there is a miss, then we need to go to the main memory and we need to bring the data. If it is a hit, then as we know, the CPU will request for only one word, right? One word, and the block contains several words. Now which word of that will be given by this word bit. So we'll pad this word bit with the line address, and we'll get the data from this particular word and we'll supply it back to the CPU, right? So that's what the procedure for direct mapping. Okay, now let us see some characteristics of direct mapping. So each block at main memory maps to only one cache line that we have already seen. And if a block is in cache, it must be in one specific location, right? And which was given by the line or R bit as far as last slide is concerned, right? Okay. Now this happens to be simple mapping. Why? Because you are given an address. Okay, you need that. Okay, go to this place, right? CPU says I need something from a particular location. If you need that, simply you go to a dedicated place given by this line address, and then you just do a tag comparison with one particular line or one particular block, right? If the tag matches, bingo. If the tag doesn't match, it is a miss, right? So it's just as simple as that, right? But as we know, there is no free lunch. As it is simple, so there has to be some problem associated with that. So for that, as I often do, I'll give you a thinking assignment, right? If a program accesses two blocks, right, that maps to the same cache line, right? The line means cache line or cache block. Then what will happen? What do you think? And I expect your discussion, your answers in the course website, and we will see, right? Okay, now moving ahead with the next kind of mapping, it is called associative mapping. So in last discussion, we saw that there is a one-to-one connection, one cache line, one main memory, right? Now this is the other way around. This says one cache block can come from rather one main memory block can be stored anywhere in the cache. Right? Initially, what was that? If there is a main memory block, right, so it will go to a particular cache block. Right? This is a fixed. There was a fixed in case of direct. But in this case, one particular block in main memory can go anywhere. Now, if that is the case, you will see that if it can go to anywhere, so that means you have to check all the locations, because it might be somewhere here, it might be somewhere here, right? So there has to be some kind of checking mechanism, right, or searching mechanism, right? And this particular tag, these are tag bits. This tag will help us so as to exactly tell whether a particular requested item is requested block rather, or rather line is actually this one or not, right? Because it can be anywhere, right? Okay, so to see this, now you have the word, because you don't need any block address to be precise, because CPU again generates some address. Now if you take out this tag bit, the whatever is however the number of lines are there, whatever number of lines, anyway you have to, it can go to anywhere, so you need to search all of these locations, right? And so the comparison logic will be complex. It is to be compared with all the lines present in the cache, and out of all the lines, if it is there, it will be there only in one line, if it is there. If it is not, then of course it is a miss. Now how do you know whether it is there or not? Well, the tag bits of the requested address will be compared with the tag bit, all the tag bits. If that matches, it's fine, right? Then on. If that doesn't match, there is a miss. So it is expensive. Why expensive? Because the comparison logic, in the last slide you saw that the comparison was done only with, there's a two comparisons, right? The requested address and tag bit of one particular block. But here it is the tag bits of all the blocks or all the lines in the cache, right? Now the last kind of mapping is something in between, right, which is called the set associative. So the first one says there is dedicated one, right? So the direct one says one to one. Associative says, well, it can go to many places, or rather all places. Now this is something in between. Beach ka hai. So as the name says, or rather as the intuition says, so it should be something in between. So don't look at all the cache lines, right? Rather look at a few places in the cache line, right? And that this particular bunch is called one set. So essentially what you have seen, that the cache will be divided into a number of sets, right? And each set will contain a number of lines, a number of blocks, as we already know. And that number is called K. So it will be a K-way set associative cache if it contains K lines in a set. So one set will contain rather a set of lines, and all the sets in the cache will contain same number of lines, right? And a given block can map to any line within a set. So now it's not like any line within a cache, it is any line within a set. So our comparison circuitry will be smaller, right? So so it is in between direct and associative, right? Okay, now if that is the case, let's say one block in cache one particular block in cache can go to anywhere within a set, right? So this is a set. Similarly, this block can go to any line within that set, right? So this is set 0, here's some set v minus 1, right? Now if you go to that comparison wala diagram, so here this is a clear-cut distinguishing between your word, the set and the tag, right? So this number of bits will tell which set to go, right? So this set number, this address will identify you to a particular set, let's say set 1. Now within that set you will have different lines. This is line 0, let's say, within the set. This is some line k, right? Now out of this, it can be anywhere within this line, right? So the comparison logic will be comparing only the number of lines. If you have x or k number of lines, you'll be doing, we'll be comparing with k tags, right? Because each line will have its individual tag, right? And the rest of the things are same. If it is there, it will be in this set only. If it is not there, it is not there, right? Even if it is supposed to be in a set, we need to check whether it is actually there in the set or not, right? So along with all these things, there is another bit we need to consider is called the valid bit. But as per to make the thing simple, we have not considered the valid bit in this case, because whenever cache a line comes from main memory, its valid bit is set to 1, right? So it's not only the tag bit. In a cache line you will have many other bits like valid bit, like dirty bit, right, and others. Okay, now we have discussed different types of mappings: direct mapping, associative mapping, and set associative mapping. As I was telling, I will come. So what was that? Let's say a processor generates 6 bit of address, right? Say okay, say 00, and then it starts with just 0000, right? So let's say this particular is my tag, this is my set, this is my word, right? Okay, now the word will have 0001 again, then 1011, right? So this comes under one. This is one set, right? So for all these words, you'll have set 0, right? And of course this will be 0. Now after some time, right, so then what will happen? You'll have set 1, again you will start from 0, right, 1011, right? Now after some time down the line, we'll see that again it starts with set 00. How come? Because in this case this bit will be different. This might be 01, right? So 0001, 1 0 1 1. So is 0. So this is one particular set. This is one particular set, right? So this is set 0. This is also set 0 because set bits are 0 0. Now, if this set can contain a cache address, a cache line with an address. Now you can see it can come from either this location or it can be this memory location, right? Now how will you distinguish? You will distinguish with the help of these bits, right? So that is the essence of our tag bit as far as mapping is concerned, right? I hope now this is more clear to you. Okay, now moving towards our discussion, you can expect a whole lot of questions in GET from this mapping, and in today's lecture we'll cover 2 such problems, right? And these problems are taken from